Okay, so this is the second part of the foundations lecture for Bayes 1. I was at the point where I had introduced discrete and continuous distributions and the basic properties of these distributions. And so let me just pull up my slides. Right, so we had looked at discrete and continuous random variables, and I'd introduced the DPQR family of functions. So now I'm going to talk about two other topics in this lecture. The first topic is maximum likelihood estimation and the notion of likelihood. And the second topic that I'll discuss is bivariate distributions and more generally multivariate distributions and how these are defined in the discrete and continuous case. So moving on to maximum likelihood estimation, one important idea that you will encounter in statistics is the idea of an expectation. And so the expectation of a random variable, so let's take the discrete case at the outset. The expectation of a random variable with some probability mass function f of y will be defined as shown in equation 12. It's going to be uh, every possible um, outcome multiplied with the probability of that outcome, right? So going back to my example of 10, asking people 10 questions, the possible things that can happen in that experiment is you can have zero correct answer, one, two, three, four. So each of those possible answers has some probability. So you multiply each of those possible numerical values, so zero correct answers, one correct answer, two correct answers, with its respective probability and sum up the result. That's what equation 12 is saying, right? So to take a simpler example, suppose we toss a fair coin just once, right? In that situation, the possible things that can happen. So technically, these are events, of course, right? I keep saying outcomes, but it's just like an oversimplification there. But these are possible events that can happen, tails or heads, right? So which we are representing tails as 0 and heads as 1. And each of these events has a probability 0.5. So remember from section 1.1 that probability is associated with events. So that's why I wouldn't call these outcomes technically, right? So, right, so each one of these events has probability 0.5, and therefore the expectation of such a random variable associated with a fair coin toss would be the result shown in 13. So the probability of success, in this case, let's say a heads, is going to be 0.5. And the way that arises, that 0.5 is the expectation of this random variable. And that arises from this summation of 0 multiplied with its probability of happening and 1 multiplied with the probability of that happening, and summing those two things up, right? So that's the definition of expectation, right? And it's the same for continuous random variables, except that in the continuous case, instead of a summation, you've got an integral sign, right? Because we're in continuous space. Variance is defined in terms of the expectation, right? And in terms of the square of the random variable, the expectation of the square of the random variable. So the definition is the variance of y is the expectation of y squared, which is the transformation of the random variable y, minus the expectation of the random variable y squared, right? So that's just the definition. All these things are discussed in, any statistics textbook. If you pick up any math stats textbook, they will introduce these definitions there, right? So, but yeah, it's important to understand what the meaning is of an expectation. So the meaning of an expectation, well, of course, I'm talking in frequentist terms right now, is that if you were to repeatedly do the experiment with a larger and larger number of trials and calculate the sample mean of the observation, right, we would get, we would approach the expected value in the limit, right? So it's an asymptotic result that The expectation is what you would get to if you kept increasing sample size. For smaller sample sizes, anything can happen, right? So, and I will just demonstrate that visually, right? There's another way to think about expectation, and that other way is to uh, think of it as a weighted mean of all the possible events weighted by their respective probability. And that's literally the definition, of expectation. It's a weighted mean, right, of each of these possible events weighted by the respective probability, right? So that's what a weighted mean is. So that these are two ways of thinking about expectation. Now, there are some analytical results in statistics which you can find in my online textbook. This one here, I also linked it in Moodle, right? So there's some analytical results for the binomial distribution and for the normal distributions, expectation and variance. For the binomial, the expectation is n times theta. N is the number of trials that you have. Theta is the probability of success. So that would be the expectation theta. This can be proven analytically. Okay? It's not just arbitrary here. And you can estimate theta from a particular sample by dividing um, k, that is the k successes that you get, divided by n, the number of trials, right? So if you have 10 successes and you get 7 correct answers, then your estimate of theta, which is usually written theta hat, right? In LaTeX is backslash hat and then backslash theta, right? This is now the estimate of the parameter theta here from the data that you have. And the variance can be computed by n times theta multiplied with 1 minus theta, right? So you can also estimate the variance given some data by just multiplying the number of trials with your estimate of theta in this equation here, right? So you can get estimates of the the expectation and the variance from a particular data set that you have. And these equations that you're seeing here for theta, this equation for theta and this equation for the variance, these are called estimators. But what you get from your data is an estimate, right? So there's two different terms. The equation itself represents an estimator, and what you get from the data is an estimate of the expectation or of the variance, right? Okay, so that's the discrete case. And in the normal case, this is probably much more familiar to all of you, right? So the definition of expectation, as I said, is in terms of an integral now. It's not the summation. So the expectation of random variable is going to be mu. This can be proven, right, through integral calculus. And you will estimate the mu. You get mu hat as the estimate. It's also sometimes written y bar. So depending on the situation, it's sometimes convenient to talk about the mean mu in the normal distribution in terms of the sample mean, right? So the sample mean is written y bar, which is also um, an estimate of mu here, right? So these two things can be used synonymously. And of course, the equation is probably known to you, the sum of all the data points that you observe divided by the number of data points that you have. That's the sample mean. Variance, which is sigma squared, right? Here in this parameter, the sigma squared gives you the variance, right? So here I should say something important, which is that whenever I talk about the normal distribution, and that's true in our entire textbook, we define the normal distribution in terms of the mean mu and the standard deviation sigma. Now you'll often see in textbooks that the normal distribution is defined in terms of sigma squared, mu and sigma squared, right? That's just a way of parameterizing a distribution. You can parameterize a distribution using one approach or some other approach. You'll see different parameterizations of distributions like this, but we are following the convention of parameterizing the normal distribution in terms of the mu and sigma because that's the way that they are defined in R, and that's the way that they're defined in the probabilistic programming language stands. So we're going to stick to that convention. But the variance, of course, is always in terms of the square of sigma, right, by definition, right? So it's important to remain clear whether you're talking about the variance or you're talking about the standard deviation, right? You have to be very clear about that. People get confused or forget sometimes that they were talking about the variance and start using the formula for the standard deviation or something, right? So the definition of variance, I also mentioned this in class on Friday, is given here, right? You can, this is the estimator, and you can estimate it from the actual data. So you can get an estimate of the variance from the actual data by using this equation here, right? So all these results, as I mentioned, are analytically derivable, and you'll see the proofs in my textbook, which is online. Okay, so um, right, so what we do typically when we do data analysis is that we start by getting an estimate of the parameter of interest. So in the binomial case, it would be theta. So we can get the estimate of theta by dividing k by n, right? Now, what's interesting about this estimate is that this estimate, theta hat, in a binomial, random variable, is going to be the maximum likelihood estimate. That's a technical term. And what we say is that theta hat is a maximum likelihood estimate of the unknown parameter theta. Right? Remember that theta is forever unknown. We're just going to estimate it. But theta hat is a maximum likelihood estimate. So the question is, what does that mean? So I'll just explain that, right? What is maximum likelihood estimation? And what is a maximum likelihood estimate? So as I mentioned, once we know the MLE, the maximum likelihood estimate, theta hat, we can compute the variance because it's defined in terms of the maximum likelihood estimate. So in the frequentist world, these maximum likelihood estimates play a crucial role in statistical inference. Everything begins with these MLEs, and all the hypothesis testing and any kind of estimation of anything that we do of confidence intervals and so on, everything is based on these maximum likelihood estimates. So, so let's try to understand what exactly is meant by maximum likelihood estimate, right? So before we can understand this term, we have to understand clearly what a likelihood function is, right? So let's go back, cast our mind back to the binomial distribution. Remember, I introduced the probability mass function, which I'm writing in shorthand here as P of k given n theta, right? And let's just assume that we know what n is, so the number of trials, which you obviously know if you run an experiment, right? On a particular experiment, you know your sample size, right? Or the number of trials. And let's also assume that we know theta, right? When we know n and theta, then this probability mass function, right? Remember, I'll just write it out again so that we don't forget what this probability mass function is. So let's go to right? So my probability mass function was something like this, right? N choose k times theta to the power of k, 1 minus theta to the power of n minus k, right? So this function is actually a function of k right now because that's the only variable here, right? I would plug in a number ranging from, let's say, 0 to 10 if I have 10 trials into that k variable, and because all the other numbers are known, I will get a probability here for that kth possible event. Okay. So this probability mass function is actually a function of k, the number of successes. But you can actually see this probability mass function as a function of theta. The same probability mass function can be seen as a function of theta, right? What that means is that when you do an experiment, let's say with sample size 10, and you get a particular number of successes, so let's say 7 successes, right? So k and 7 are constants now, right? The data are collected. They're no longer variables in any sense, right? So what's the third variable that's left? And that's theta. So you can think of this whole function, right? So you can, in this particular case, you can think of this function as a function of one variable only. And that one variable is theta, right? So this function now is called a likelihood function because it only depends on theta, right? And it's written with this. I think this is a MathCal L or something like that. The LaTeX thing is MathCal. I don't know. I've forgotten how to write this. Okay. So in any case, you can look it up. So this curly L is used to represent the likelihood function. And so it's sometimes written this with this curly L theta given K and N, right? So in this case, K and N are given because now the data are collected. They're constants. And therefore the function, the same probability mass function that we used for calculating probabilities of different events, the same probability mass function is seen now in a different light as a function of theta. So we sometimes write it like this, likelihood theta given kn, or you, because kn is now understood, we will often write the likelihood just L theta, right? Because everything else is understood anyway, right? So that's, here's an example, right? I've got the likelihood function laid out here for this particular example that I'm discussing. And what we can now do is into this function, we can plug in different values ranging from 0 to 1 because theta is a probability, right? It can be any real number between 0 and 1. So I'm going to plug in successively different values of numerical values for theta ranging from 0 to 1, compute this number, and then plot all the theta values on the x-axis and the resulting likelihoods on the y-axis. And if I do that, I get a curve like this. Notice that the x-axis ranges from 0 to 1. And this curve, this characteristic curve in this particular experiment, we have 7 successes out of 10. What you will find is that this particular curve peaks at a particular point, and that particular point is zero point 0.7. And it's peaking at that particular point because zero point 0.7 is 7 divided by 10, right? Remember the maximum likelihood estimate of the theta parameter is k divided by n, and k divided by n in this case is zero point 0.7, and that's why this curve is peaking here, because the k divided by n turns out to be the maximum likelihood estimate. And what that means is that it's the most likely value. Zero point 0.7 is the most likely value of theta given the data that you've observed. It's not necessarily the true value. It's just the most likely value, right? Given the data, right? So this function is called the likelihood function. It's not a probability density function because the area under the curve need not sum to 1, but it's just telling you what the most likely value of the parameter is given the data that you have. So that's the meaning of, the maximum likelihood estimate, k over n in this case. It's telling you the point on the x-axis where this curve is at a maximum point. Okay? Every other value of theta is going to be less likely, right? So the maximum likelihood estimate, MLE, gives us the most likely value that the parameter has given the data that we have. And as I said, in the binomial case, we have this equation. And in the normal distribution, we have the equations for mu and sigma. So they give us the maximum likelihood estimate. Okay? More details on this, of course, are in my lecture notes, the LM linear modeling lecture notes, but also in this textbook that you can read by a mathematician called Cairns. This introduces probability theory and statistics using R. So it's an interesting textbook, which I would recommend if you want to know, want to get another, um, perspective on the theory that I'm quickly working through in these lectures. So one last thing I want to say about maximum likelihood estimation is that I just want to stress the fact that the maximum likelihood estimate is going to lead you to the expected value, so the true value of the parameter in the asymptotic case. So what I'm doing on the x-axis in this figure is that I'm steadily increasing sample size. It's on the log scale, so I'm getting larger and larger samples. And each time I take a sample from a particular, let's say, a binomial distribution, I'm going to get a maximum likelihood estimate each time for every sample size. Those are the dots that you're seeing. But those maximum likelihood estimates are going to be fluctuating around the true value. So suppose the true value is 0.7, then because of random variability, what will happen is that the maximum likelihood estimate is going to fluctuate as we repeatedly collect data. But as we keep increasing sample size while we're repeatedly collecting data, what you notice is that this fluctuation around the true value of theta that we're seeing with these maximum likelihood estimates, it settles down and starts landing exactly on the true value of theta. So asymptotically, these maximum likelihood estimates will get you to the true value in the limit. Now, obviously, we are never going to have infinite data, right? So this asymptotic result is a theoretical result. In practice, what's going to happen to us is that we're going to be in a world like this, where the maximum likelihood estimate is going to be, could be, right? It need not be. So you could have a maximum likelihood estimate that is very close to the true value. You see that here in this example, right? But you could equally well have a maximum likelihood estimate that is very far away from the true value, right? So that's the nature of random sampling, that we get a lot of variation in the data. So it's not necessarily the case. That's why I'm trying to hammer on, repeatedly rant about this point. It's important to understand that from a single experiment, when you get an estimate of the MLE, it's not necessarily the true value. You just don't know. Okay? So all right, so I won't repeat the summary here. You can take a look at it because I've released the slides. Let's move on to the next topic. The next topic is bivariate and multivariate distributions, right? So bivariate distributions have the property that, let's look at discrete distributions first. So the example I've taken is from one of my students' dissertations. I have in each trial, in this experiment, I'm getting two measurements. One measurement is a Likert rating, so a discrete rating ranging from 1 to 7. And the other measurement that I'm getting is an accuracy response, like a 0, 1 response. So the accuracy response is the familiar binomial distribution. The Likert ratings is going to need a different distribution to describe it. The possible events that can happen range from the numbers 1 to 7. It will need a multinomial distribution. That's a distribution that we will discuss in the second part of the Bayesian course that I teach in the summer. Okay. So, um, so what we have is two measurements in every trial, and the the way I would characterize the probability distribution of giving each one of these 0, 1 responses and each one of these 1 to 7 responses would be through a bivariate distribution. So what we're talking about here is a distribution that represents the joint distribution of these two sets of random variables, x and y. Right? This is the joint distribution now. So mathematically, so graphically, you can see what it looks like, right? So I can see, for example, for the Likert rating 1, the probability distribution for 0, 1 responses are these two bars here. For the Likert rating 2, there are these two responses, correct and incorrect responses, and so on, right? You can see this. So intuitively, if I look at this plot, what I can see is that there is a higher proportion of correct responses overall than incorrect responses, and there's there's an increase in the proportion of correct responses when the Likert rating goes up. When the probability of a 7, for example, oh, sorry, let me say that again. When a Likert rating is 7, then the probability of a correct response is higher than when a Likert rating is, let's say, 1 or something like that, right? So that's what this plot is showing us. This is the joint distribution of two random variables, x and y, and this is a bivariate discrete distribution, right? We would write this joint probability mass function. So we can characterize this mathematically, and we would write a joint probability mass function as pxy. So that's the two random variables. And these are the two possible things, that can happen, the two possible events that can happen, right? So as in a tabular form, we can summarize the probabilities. These are empirically derived from the data, right? So we have observed the data and we can calculate the probabilities like this. So this table represents the empirical probabilities from the actual experiment that is reported in this dissertation. And so what we see is for each of the Likert values, there are probabilities for 0 and 1 correct responses. So this is the joint distribution written like this of the two random variables. Now, um, from the joint uh, probability mass function, this one here, what we can do is we can compute two useful quantities. So one useful quantity is the marginal distribution of the random variable x and of the random variable y. So the definition of a marginal distribution is the following. So these are given in equation 16 and 17. So if I want to compute the marginal distribution of the random variable x, that means I want to compute the marginal distribution of this random variable with these possible events. Then what I'm going to do is I'm going to sum up each of the values in each of these 7 columns, right? I'm going to sum these values up, right? And that's what this equation is doing here. It's taking the joint probability mass function and summing up all the values along the columns, right? So once you collapse, sum up these numbers, you're going to end up with the marginal distribution of the random variable x. Basically, what the reason it's called marginal distribution is that you're marginalizing out the y values here. Okay? And similarly, you can get the marginal distribution of y, right, by summing over all the x's. So what that means is, to get the marginal distribution of y, I'm going to sum up all these values for the value 0, sum up all these values for the value 1, right? These are the definitions, of marginal distributions. And it makes sense, right? That it tells us ignoring the other variable. If I want the marginal distribution of x, I'm ignoring the other variable y. That means I'm summing over all the values. And similarly, for the marginal distribution of y, I'm summing over the other variable that is x here, right? Okay. So that's, I think this is what I've done here. Yeah. So, oh yeah, right. Sorry. Actually, maybe I misspoke earlier. The marginal distribution is called the marginal distribution also because it appears in the margins here. You see this? It's also in the margins of this table now, right? This is the marginal distribution of y, and this is the marginal distribution of x. And notice that these numbers have to sum up to 1, and these numbers have to sum up to 1 because they represent the total probability of what can happen, right? So you can check that these numbers do sum up to 1. It's possible that they don't sum up exactly to 1 because of rounding errors, okay? But if you were to run the code that lies behind, I created this table dynamically in our Markdown, and I gave you the source code, I think, for this. So you should be able to reproduce the summations as coming out to 1 if you don't do any rounding. Okay? But technically, they should round up to 1. Okay? Right. So graphically, marginal distributions you should visualize them always mentally because they're easier to understand that way. So the marginal distribution of y, the random variable y, is basically, looking at this distribution from this side, looking at this three-dimensional plot from this side, and the marginal distribution of x is looking at the three-dimensional plot from this side, right? That's why you end up with this plot that only represents the 0, 1 responses, right? Y equal to 0, y equal to 1, and the probabilities of those, which should sum up to 1. So this is a discrete distribution again. This is a probability mass function that represents all the possible things that can happen. Similarly here, because I didn't have too much space, I'm only showing some of the random variables here. Here you're seeing the probability distribution, and this is basically the landscape that you're seeing when you're looking at this plot from here, right? So that's why you see this characteristic shape with higher values of x, you get a higher probability. All right, so the conditional distributions, that's the second thing you can get out of a joint probability mass function. You can get the conditional distribution of x given y, or the conditional distribution of y given x, right? Now, hopefully you remember the definition of conditional distribution from the lecture notes, right? The definition is in equation 18 and 19 here for each of the two conditional distributions. So the conditional distribution of x given y, which is written like this in equation 18, is going to be the joint probability of x and y divided by the probability of y, right? That's the definition of conditional probability. So you can use this equation now to compute the conditional distribution. Again, that's a probability mass function that you're computing given a particular value of y. So here, what we're going to do is we're going to set y to either 0 or 1, right? Because y can have value 0 or 1, and then compute the distribution of y under those two conditions, okay? Similarly, for y, for the conditional distribution of y given x, for each possible value of x, we're going to fix particular value of x and compute the distribution, right? So um, I'm going to do this for one case, and then you can fill in the rest of the conditional distribution table, okay? So for one case, we'll do it like this. What we're going to compute is the conditional probability of getting x equal to 1, given that you have y equal to 0. Okay. So looking up the conditional probability rule, the way to compute this conditional probability would be to take the joint probability of 1 and 0 happening, that's this number here, and dividing by the probability of 0 happening from the marginal distribution of y, okay? Because remember, here we're working with the marginal distribution. So the main point here is that in order to compute a conditional distribution, you need to know the marginal distributions, right? You can't compute the conditional distributions without knowing the marginal distribution. So whenever you're asked to compute the conditional distribution, you have to first figure out the marginal distributions, okay? Because you need them in the denominator, right? And so anyway, here we go, right? So I know from the marginal distribution of y that the probability of observing y is 0.291. So I've got my numbers, 0.018 and 0.291. So I divide 0.018 by 0.291, and I get the probability for this particular set of outcomes, right? And now I'm going to just keep doing this for different values of x, and that's going to give me a set of probabilities. Yeah, look here. So for, what did I say? For y equal to 0, I filled in this number for you, but now you would have to do the same calculation for 6 other values, right? That would fill in these numbers here. Then you would start over by setting y equal to 1, and then looking up the marginal distribution of y equal to 1, that's 0.709. That would be in the denominator now. And then in the numerator would come all the values for different values of x, just like here, okay? So you just have to do this exercise on your own. Make sure that you compute, fill out this table in your own time. I won't be checking it, but it's a good exercise. It gives you a good feel for, how the conditional distribution is defined. And once you fill out this table, you have the conditional distribution of x given y and the conditional distribution of, you don't have the other one. To do the other one, you would have to reverse everything, right? So as an extra exercise, you could compute the conditional distribution of y given x. All right, so that's the discrete binomial case. And now I'm going to turn to the continuous bivariate case. Sorry, I misspoke there. It's the discrete bivariate case. So now what I want to talk about is the continuous bivariate case. I'm not saying anything about multivariate distributions yet, but multivariate distributions, both in the discrete and continuous case, are generalizations of the bivariate situation. So once we understand the bivariate case, the multivariate case is just more of the same, right? So let's focus on the bivariate situation. Now, for the continuous case, I want you to consider two random variables that are normally distributed. So call them X and Y. And let's say that each of them is coming from a particular normal distribution, a standard normal with mean zero, standard deviation one, right? Also, let's assume that there is some correlation rho between them, right? So what I mean is, let me show you graphically, right? So um, going back to my iPad, right? So if I have two random variables X and Y, it's possible that there is some association between these two random variables. So it's possible that there's some positive correlation between them. So the way we would characterize that is by a parameter called rho. This is pronounced RHO. It's a Greek letter. Looks like a P, but it's actually pronounced rho. And in order to be completely, explicit, we often write, sorry, we often write X, Y, right? But because X, Y is understood, I will often, just drop it and just call it X, Y. Okay. So let's just call it for now, let's just call it X, rho X, Y. But just be aware that I will drop this when it's understood. Okay. All right. So that's one possibility. There could be a positive correlation right here, but there could have been, a negative correlation or no correlation at all. So a negative correlation would look like this, something like this, right? So X and Y. So here rho is negative, right? And a third possibility is that the association is like basically not there, no correlation between them, right? So these are the three possible, um, discrete cases that one could be thinking about. But of course, correlation, as you are probably aware, is a numerical value that ranges from -1 to +1, right? So you can only get values ranging between -1 and +1, right, in correlations. This will become relevant later on, right? So anyway, so basically we're talking about two random variables, two standard normal distributions, and we want to express somehow the fact that there may be some correlation rho between them, right? And I will show you some visualizations of this in a moment, okay? So that you can imagine what this looks like. So basically, in statistics, the way we talk about bivariate distributions is as follows. So we're going to mathematically, we will write a bivariate distribution like the one I described. So I'll write it out explicitly. X is a standard normal, Y is also a standard normal, right? And so what I'm saying is the correlation between them is rho, right? So this is the information I need to encode mathematically. The way we are going to do this is in matrix form. We're going to write that the 2 by 1, 2 by 1 matrix XY represents the bivariate distribution. And this is coming from a bivariate normal, right? That's what this _2 says, with means 0. X and Y means 0. And the variance of the first random variable is whatever this variance is. So I'll call this 1 squared, right? And the variance of the random variable Y is given in the lower diagonal here, also 1 squared, right? Because they're both 1 here. And in the off diagonals, that's this thing here. What I'm going to write is the correlation times the two standard deviations, right? So correlation times the two standard deviations, right? Now, because 1 times 1 is just 1, so I'm just going to write rho here and rho here for this particular example, okay? Just for this particular example. So this quantity and the off diagonals is actually called a covariance, and it represents, it's the definition of covariance is sigma times sorry, rho times sigma x, sigma y for the bivariate case, right? So the covariance appears on the off diagonals and the variance appears on the diagonals. This is the diagonal. So this matrix is often written in shorthand as big sigma, okay? And this is called a covariance matrix, okay? So, um, so the way we characterize a bivariate distribution, like the one I'm just talking about, is in terms of this general mathematical form that we have some mean for the x random variable and some mean for the y random variable. This does not have to be zero, right? It depends on what the underlying distribution is, and some variance covariance matrix here. This is how we will summarize a bivariate distribution. Yeah. So, so this is what I've written out here, right? I've just written out the variance covariance matrix here, so you can see what it looks like. And now I've explained the definition of covariance here, right? Okay, so notice though that the joint probability density function of these two random variables is now described by this function. So there's actually an equation that you could write down that represents this function. I'm not showing it, but you could do that. And so one of the properties of this joint probability density function, right? You can imagine that there's a continuous version of this discrete example. This discrete example, we are thinking in continuous space now. I'm just going to show you a visualization, but this is now smooth surface of some kind, a three-dimensional surface, and the volume under the surface has to sum to one because it's a probability density function. It's a joint probability density function, right? So it has that sum to one property because it represents the area under the curve represents the probabilities, right? So the volume under the curve would be computable using a double integral, right? So we're going to integrate with respect to x and y, and we're going to integrate the joint probability density function. And the stipulation here is for this joint probability density function to be a proper probability density function, the area under not the area, um, the volume under the curve has to sum to one. Okay. So similarly, we could also compute the cumulative distribution function in a bivariate situation. And the way this would work is what we would be computing is the probability of observing some value u or something less than that in the random variable x and some value v or something less than that in the random variable y. And the way we would compute it is exactly the way we computed in the univariate case, except that we have to integrate with respect to y and with respect to x, right? So what we are doing is we are integrating for the upper bounds u and v with respect to y and x, and so um, we get the cumulative probability of observing u and v or something less than that, right? So basically, this is just a generalization of the univariate case, nothing complicated going on here, right? And the marginal distributions can also be computed in the continuous case, and they're done in exactly the same way as the discrete case, except that the summation is now is an integral. So for the marginal distribution of x, I'm going to integrate with respect to y, and for the marginal of y, we will integrate with respect to x. It's pretty straightforward, right? If you want to see some examples of this being done, by hand, then the textbook by Cairns that I mentioned, this textbook, I'll just write it out. There's a textbook by this guy called Cairns. You can Google for it. The book is called Ipsur, right? It's a shorthand abbreviation for the textbook. It's freely downloadable. He gives some nice examples of how to compute marginal distributions from continuous bivariate distributions, right? So that will give you a good intuition if you know some calculus, right? If you don't know any calculus, it doesn't matter because all I'm doing is what I did in the discrete case. I'm just summing in continuous space. That's what this integral is doing. So conceptually, it's the same thing. So this is what the continuous, bivariate normal distribution will look like, right? So the X and Y values here are representing the support of the two random variables, right? And what you're seeing here in the lower plot is the cumulative distribution function. You can see that it's rising up to 1 here, right? And whenever we compute the probability of observing some number like u on the x side and some number v on the y side or something less than that, we're computing the volume under this curve here, right? Through integral calculus. And so that's the cumulative distribution function you're looking at. And that's a contour plot on the left, which shows, you know, the steep rise of the CDF. And what you're looking at the top plot here is the joint probability density function of these two random variables. And you will notice that this is the case where rho is equal to 0. In other words, the correlation between the two random variables is 0. In that case, what you will observe is a smooth cone which has exactly symmetric shape no matter how you turn it or look at it. It doesn't matter how you look at it, it's going to have the same symmetric shape. And you can see that in the contour plot as well. That's the case when you have zero correlation. Okay. If you have a negative correlation, so I just chose minus 0.6 as an example, you will see this contour, the negative, relationship between X and Y, and the shape of the smooth, symmetric shape of the cone will compress along this axis here. So that's what you're seeing here. And similarly, if the correlation is positive, then you will see the cone compressing along this axis here, right? So the shape of the distribution is going to change depending on the correlation parameter here, okay? So one important thing to get a handle on, with bivariate and multivariate distributions is to know how to generate simulated data from a bivariate distribution. So what we're going to do is we're going to define a variance covariance matrix, which I'm calling big sigma here. So what I'm doing here is that I'm creating a matrix, right? So what I'm doing here is I'm creating a 2 by 2 matrix. You see that? This is a 2 by 2 matrix. And what this matrix is, I'll first write it out and then I'll show you what this matrix is representing. In the top element, I've got 5 squared. At the bottom diagonal, I've got 10 squared, right? And in the off diagonals, I've got, what is it? 0.6 times 5 times 10, right? So 0.6 times 5 times 10. So the matrix I'm trying to build here is this one here, right? And so I'm using the matrix function in R, and I'm defining what comes here, and what comes on the off diagonals. So that's what I've done here. And so if I run this code, I'm going to get a 2 by 2 matrix, which is this big sigma. And then what I'm going to do is I'm going to take this package mass. So perhaps you have to install this package in R, right? I hope you guys know how to install packages in R. You have to go to Tools and go to Install Packages and then type something like, I don't know, what was it? Mass, right? If you type mass and hit install, it's going to install the packages for you, okay? So having installed the mass package, there's a function in it called multivariate R norm. So it generates random, normally distributed multivariate data with arbitrary dimensions. So in this case, we are generating data from 2 dimensions. So a bivariate distribution. We are assuming that the mu is 0 for the 2 random variables, but the variances are not 1 in this case. I just chose some larger numbers like 5 and 10 for the 2 random variables, right? So I'm generating 100 data points, so 100 pairs of data. because it's a bivariate distribution. I'm generating 100 random data points from this distribution, having defined mu and sigma. And what I get is a 100 by 2 matrix, right? So this is one set of data points for the X and Y values. This is another set of data points for the X and Y values and so on, right? And this is what it looks like graphically. And so what you'll notice is that there's this distinctive positive correlation that you're observing between these. This is coming from the fact that I stipulated that the correlation is 0.6. If I'd set this as at minus zero point 0.6, then this plot would look very different. So let me see if I can do that for you here. Yeah, let me just run this code, okay? So I'm just going to copy this code and produce some data. Let me kill this, sorry. Um, Sorry, I was editing the book right now. So let's run this code. I'm going to create this big sigma. So let's look at it, right? So this is 5 squared, this is 10 squared, and this is the correlation here. 0.6 times 5 times 10 is 30, right? And so then I'm going to multiply, create the random data, okay? 100 data points. This is a 100 by 2 matrix, 100 rows, 2 columns, right? And so I can now plot this matrix, X and Y values, right? And so if I plot them, you'll see this distinctive positive correlation here. And if I change this correlation to minus zero point 0.6, let's say, right? Minus zero point 0.6. Yeah, right? Now what's going to happen is my sigma looks very different, right? Look, let's look at sigma again. It's got minus 30 this time, right? Because the correlation is negative. And now if I generate some random data, I'm going to see that the correlation is actually flipped completely, right? So you're seeing that distinctive compression of the bivariate distribution here, okay? Similarly, if I were to set the correlation to 0, let's see what's going to happen now. You will see when I set the correlation to 0, the first thing to notice is that the big sigma, the off diagonals are 0 now, right? That represents 0 covariance, right? And so now if I generate some random data and plot it, you will you will notice that there is basically this circular blob that you have, provided you have sufficient data, okay? So like if I had 10,000 data points, then you'd see a very, very distinctive blob here. But it's easy to get fooled, okay? Fooled by randomness. If I had just 10 data points, okay? If I were to repeatedly generate random data like this with no correlation, okay? Surprisingly, every time I generate some random data, every now and then I will see a surprising correlation between those 10 data points. Does this look like no correlation? Yeah, I would say so, right? But let me run it again, right? Also looks pretty random here. But if I keep running it, I can end up seeing some correlation, that looks tantalizingly like a positive or negative correlation. Let me just do it a few more times. Here, you see that? So here I've got, this is looking very tantalizing now for me. But those three extreme values here, they kind of cast doubt on that. But if I just concentrate my mind on these 7 data points, this looks really tantalizingly like a positive correlation, but it's coming from a bivariate distribution with 0 correlation. So you will often see papers publishing, some correlation with 10 or 12 data points that look tantalizingly like a positive or negative correlation. And it will even come out significant. Okay, so let me just show you. So let me first compute the correlation between these two guys. Let's see what it looks like. Let's compute the correlation. Okay, that's actually, these values have pushed it down. So let me see if I can create some really nice fake data that actually looks correlated. Nice. This is a good one, right? So I've got a 36% correlation here, right? 0.36 correlation now. And so if you were to compute a linear modeling, fit here, you may well find some relationship between, you know, um, it can happen that you will find a relationship between U1 and U2. Let's see what happens, okay? Just fooling around here. Oh, sorry, did I do this wrong? Oh gosh, I forgot to. Right, so, okay, luckily this did not come out significant, but it can happen that this starts looking like a significant effect or something like that. So, so the important point here is that a sample size of 10, a small sample size can end up, being showing you misleading correlations. Probably the mistake I made here for generating random data is that I should have had larger standard deviations. You can try that. If you increase the standard deviation, allow some more room for variability, you will see occasional, positive or negative correlations. Anyway, so that should give you a good intuition for what a bivariate distribution should look like, what its components are, the standard deviations, control the spread, on both random variables, and the correlation determines the relationship between them. So, this foundations lecture is very important because in the coming weeks, we'll be working with such bivariate and multivariate distributions. And it's very important to understand what a discrete and continuous random variable is and what the associated probability mass functions and distribution functions are, because we'll be operating with those and we'll be um, um, multiplying those distributions, those likelihood functions, like the binomial likelihood function I showed you, with another distribution, the prior distribution for the theta parameter, to get the posterior distribution. So these foundational ideas are extremely important for doing the rest of the course, right? So please make sure that you fully understand the following topics: what a probability mass function is, what a probability density function is, and the DPQR family of functions associated with them, right? You have to keep in mind what a likelihood function is. It's just the probability mass or density function seen as a function of the parameters in that function, instead of being seen as a function of uh, the observed values or something like that, right? Then in the bivariate case, you should be clear about what a joint, marginal, and a conditional distribution is. And of course, I only introduced the bivariate case to you, but later on we will generalize beyond the bivariate case to multivariate cases. So let me quickly, as a last point, just show you what an example would be of a multivariate distribution. So we could have three random variables, x, y, and z. Okay. So now this is the continuous case. So now we have a normal distribution with three dimensions, right? So assume that the means of these three random variables is 0. Now we are looking at a variance covariance matrix that's going to contain that's going to have dimension 3 by 3. So this will be a 3 by 3 matrix. And along the diagonals, it will contain the variances of these three random variables. And along the off diagonals, these off diagonals, right, it will contain the covariances. So this first box will contain the covariance of x and y, right? So I'm just writing it C because I don't have enough space. This one will contain the covariance of x and z, and this box will contain the covariance of y and z, right? And the same thing will happen here because this is a symmetric matrix. You will get the covariance of x and y here, the covariance of x and z here, and the covariance of y and z here, right? Right, exactly. That's what you will get, right? So basically, this variance covariance matrix will look like this. I need enough space to write this, so it will look like this: sigma x squared sigma y squared, sigma z squared, right? On the diagonals. Then we get rho x, y. Now it's relevant to have subscripts for the rows because there's going to be 3 rows, okay? So rho xy times sigma x, sigma y. Then we'll have here um, rho xz, sigma x, sigma z. And here we would have rho yz, sigma x, sigma z. And on the off diagonal, on the other side, we're going to have rho xy, sigma x, sigma y. So sorry, this was supposed to be a y. So these are the same two quantities here, okay? Same two quantities, right? And so this would be x and z, right? So rho x and z here, sigma x, sigma z. And so these two guys will be the same. And then I've got rho yz, sigma x, sigma z, right? So this one and this one, they will be identical, right? So that's my variance covariance matrix in a multivariate setting where I have 3 random variables. Now, in data analysis, we can easily end up with 8 random variables correlated with each other. Okay, so we are then looking at, I'm going to label it like this, U1, U2, U3, U4, U5, U6, U7, U8. These are my 8 correlated random variables. This insane world is going to turn up all the time in data analysis, especially when we are looking at repeated measures data, okay? This will be a normal situation to be stuck in an 8-dimensional world with 8 mu's and a variance covariance matrix that's going to be 8 by 8. It's going to be an 8 by 8 variance covariance matrix. So this complex world is what we will end up with in chapter 5, right? So that's why it's very important to be very clear about how you build up a multivariate distribution, right? That's the relevance of this foundation chapter. Okay, so hopefully these topics are now clear. And of course, when you need these topics later on, you can always go back and reread the chapter to remind yourself about how these things are built up. So that will help you later on. So you don't have to literally memorize anything right now. It's just good to have made a first pass through these ideas and be ready for them when you need them later on. Okay. So the next topic I will discuss in my next set of lectures, which I will record on Tuesday, will look at the foundational ideas in Bayesian modeling using some analytical results such that we can do the actual statistical inference. We can do it on paper, so to speak. We don't actually need any computational tools for the next chapter. And once we're done with that, I'm going to switch to computational tools, MC methods, because we'll start working with increasingly complex data, and we will no longer be able to do the analytical inference that we can do in chapter 2. We won't be able to do that anymore because it simply involves too much math that even mathematicians won't be able to handle. So we will switch to computational tools from chapter 3 onwards. So that's where we are going with this. I think that's it for now, and I'll see you in class.